Hi everyone, Mr. Boltri bringing you video 2.7, where we're going to be talking about pulleys and springs. So, to talk about pulleys and springs, first I'm going to give you some tips and tricks for how to address a pulley problem. And then I need to make a quick clarification on the acceleration due to gravity. To close the video, we're going to run an experiment that will hopefully give us the equation for the spring force, which I'll also sometimes call the elastic force. So, to dive right in, to talk about pulley problems. We've already done pulley problems, including the first lab that we did in this unit and the first FRQ. So a pulley problem is basically characterized by if you have some masses that are hanging over a pulley and they're experiencing some sort of acceleration. So in order for these problems to work, more often than not, pretty much always, we're going to need to have a massless, frictionless pulley. And sometimes you'll see words used like light and smooth, and those are meant to indicate massless and frictionless. But that works because if the pulley was not massless or not frictionless, then we would have to account for the mass and the friction of the pulley, and the problem would become way harder, if not near impossible for our purposes. So if the pulley meets those conditions, then we don't have to worry about its mass. We don't have to worry about the friction. Basically, what the purpose of the pulley is doing in this problem is it is changing the direction of the force. It is causing the force to be propagated over this string. So now there's the force of tension, which is pulling up on the M1, or the big M, and also pulling up on M2. So it changes the direction in that way, which then is also going to cause things to accelerate in interesting ways. For example, if big M is accelerating downward, then little m can be accelerating upward because of the pulley. So tips when you're addressing these problems. Tip number one is that when things are tied together, assuming the string is not getting longer or shorter, then the objects are going to have the same acceleration. So if we calculate the acceleration of big M, then we're going to also know the acceleration of little m, and vice versa. Which actually gets me to tip number two, which is it's often helpful to look at the force diagram for big M and little m separately. Because if we can look at the net forces on big M and we can look at the net forces on little m, then according to the F net equals ma, or Newton's second law, the net forces on big M times should equal the acceleration times the mass for big M, and then the net forces on little m should equal the acceleration, but that same acceleration times the mass of little m. And then we can have a system of equations that can allow us to solve for acceleration. Sometimes, not often, but sometimes it might be useful to look at the MM system. And by that, I don't mean the wrapper. I mean the system of big M and little m together. But more often than not, it's going to be more helpful for us to look at big M in one force diagram and little m in another force diagram. And then look at the net force on those, the sum of the forces, and then try to figure out the acceleration from there. Another tip, if you do have trouble distinguishing between when you're writing big M and little m, which some people do, and this goes for any two letters or that you have trouble distinguishing between, or that you feel that somebody reading your work, like a grader or me, your teacher, might have trouble distinguishing between, you can establish a key for the problem. You don't have to use the symbols that you're given. You can say that big M equals M1 and little m equals M2, and then from then on you can use subscripts M1 and M2 if you struggle writing big M and little m, or if you worry about your grader being able to tell the difference between those two. And the last tip is in terms of figuring out the direction that we should make the positive direction for various problems. So in this problem, what would you make the positive direction? So some people might say, I'd like it to be up and to the right because that's what I'm used to using. That's what we're used to using. Some people might say, oh, well, if M1 is going to be heavier, then we want to make down the positive direction just so that things are moving in the positive direction. If M2 is heavier, then we may want to make the parallel direction to the ramp the positive direction so that M2 will just be going down the ramp. And these are all good choices. And the key here is that you can choose the positive direction, and sometimes you can be a little bit sneaky with your choices. So if M2 is heavier than M1, then we can say up and also down and to the right, parallel to the ramp, are going to be our positive directions for this problem. So that's good because then M1 is going to be accelerating in the positive direction and M2 is going to be accelerating in the positive direction. And if M1 is heavier than M2, then we can say down and up the ramp and to the left is parallel is our positive direction, which is also good because then they're both going to be accelerating in the positive direction. And this is important because in problems like this, it's really common, really easy mistake to make is to mess up the direction of the object. So if we add an extra negative sign in there where we shouldn't, then the problem becomes wrong because we are subtracting something that we were supposed to have been adding. So to do that, always, always, always mark which direction that you are having be the positive direction. And it can be around the pulley like this, which this means that up and to the left, parallel to the ramp is positive, and also down in the vertical direction is positive. So both of these are going to be moving in the positive direction. So that actually gets me to my next point, which is the acceleration due to gravity and the negative signs that we might be adding in or not adding in when we need to. So I've actually been watching some videos to kind of clarify my knowledge of not only physics, but how to teach AP Physics and some common mistakes that AP Physics students make. And I've learned one thing, is that the definition of the acceleration due to gravity is little g. The acceleration due to gravity is defined as 9.8 meters per second squared. And that is a scalar value. It's not saying that the acceleration due to gravity is 9.8 meters per second squared in the up direction. It's just saying that that is the magnitude of the acceleration due to gravity. And because it's not universal to say that the down direction is negative, depends on the problem, you get to determine which direction you want to be positive and negative. So for our purposes, in a free fall problem, if we say that the downward direction is negative, then the acceleration due to gravity in the y direction, the acceleration in the y direction is going to be negative little g, which is negative times that value, which is the accepted value for the acceleration due to gravity. It's going to be negative 9.8 meters per second squared. So just to make sure that when you are using the symbol g, that is a positive number. It's a scalar value. And if you want to indicate the direction to be down, then you have to put a negative in front of the g. So that's kind of the opposite of what I've been saying so far. So I wanted to make sure to very clearly emphasize that this is a scalar positive value. And if we want to show that's the negative direction, we have to put the negative sign in front of it. So make sure that you're including negative signs when you need to show that something is moving down or in the negative direction. So now to transition to a new thing, let's talk about the spring force. So when we think about the spring force, hopefully you think about a whole bunch of springs. The thing about springs is that they can either stretch or they can squish. So we're going to be using both compressive and stretchy springs, but also springs are the only thing that can stretch or squish. You'll also notice that rubber bands and a whole bunch of other examples meet the criteria for the spring force, which is why sometimes I call it the elastic force also. But if in any source where you see spring force, it also applies to rubber bands too, and other things that follow the law that we're about to discover in the lab that we're about to run. But to distinguish the difference between a spring force and a tension force, we have to look at the medium. And so if the medium, which is basically the thing that is doing the pulling, either the rope or the string or the rubber band, if the medium is stretching, then it's going to be the spring or elastic force. If the medium is keeping its length constant, then it's going to be the tension force. And that's how we tell the difference. So now we would love an equation to quantify the spring force. So to do that, I'm going to run an experiment where I have a spring and I'm going to try to increase the force that the spring is exerting. I'm going to increase that by just continually adding mass to the spring. So in order for the object to stay at rest, so to maintain a constant velocity, we know the forces have to be balanced. So the spring force is going to equal the gravitational force. The spring force going up and the gravitational force going down. So as I increase the mass, I increase the gravitational force, I increase the spring force. And then we get a graph that looks a little bit something like this. If I graph the spring force versus the length of the spring. And you'll notice that it has this weird horizontal intercept. So I want you to sort of stop and think and explain what is the meaning of that horizontal intercept. And hopefully you got that, well, At the beginning, the spring is not exerting any force. We are making a big assumption in that. We are assuming that the spring is functionally massless. We know the spring does have some mass, and then therefore the top of the spring is exerting a force on the rest of the spring, and this we can sort of integrate the force all the way down because we know the bottom of the spring is exerting basically no force. So there's a lot of force up here and getting to less and less and less force down here. But if we make the easy assumption that we can neglect the mass of the spring is negligible, then we can basically say that right now it has a length of 10 centimeters, but it's exerting no spring force, which is what this means. The length is 10 centimeters, but it's exerting no spring force. But that's not going to be really useful for us to make an equation. So what we're going to do is we're going to subtract the initial length of the spring just to shift everything over to the left. So then we get the length of the spring minus the initial length, and then we get this nice linear graph that goes through 0, 0. So that's actually what we're going to use to make our equation. But instead of having length of spring minus the initial length, we're just going to call that the stretch. And we're going to use delta x to show the stretch of the spring, which is how far it is from its rest position. And rest position was the just sort of the default length of the spring. So now using y equals mx plus b, I can get force spring equals the slope times the stretch, which is exactly what I have here. Force spring equals k, which we're using as a symbol for the slope, times the stretch. And k is going to be something called the spring constant. The units of the spring constant are going to be newtons divided by meters. It's basically serves like the coefficient of friction. It's like a multiplier. The higher the spring constant, the more force friction at the same stretch. So some spring constants, the springs that I have in the back have spring constants of 5, 10, 15, and 20. So 5 newtons per meter versus 20 newtons per meter. If I were to stretch them both 1 meter, one would exert 5 newtons of force, not very much, and one would exert 20 newtons of force, quite a bit more. But the one thing I do want to point out about this equation is it only gives us magnitude, not direction. You'll see that I've left off the vector notation above force spring and stretch. So if we think about the direction of the force, if I pull a spring down, if I pull it down, then it's going to exert a force up. But if I pull it up, it's going to exert a force down. So the force is actually always in the opposite direction of the stretch. So we can say if we want to actually add the vector bars, the direction of the force friction is equal to the spring constant times the stretch, and always in the opposite direction of the stretch. So this is called Hooke's law, and it applies to all springs and other elastic material that complies to Hooke's law. There are some non-Hookean materials that do not conform to this law. Maybe it's times stretch squared or the square root of stretch, and they might give you a problem with a non-Hookean material just to see if you can linearize the graph. But any spring that's following Hooke's law, which is this, is going to just be a linear function where the force of the spring is linearly proportional to the stretch of the spring, and the slope is going to be the spring constant. So we're going to do some problems in our next class involving pulleys and springs, especially pulley problems, because AP loves those pulley problems. They love to tie things together with a string and then see how they accelerate. So we're going to practice that plenty in our next class. Please make sure you let me know if you have any questions. And until then, as always, go Bears.